over the topic of neural network in machine learning. As we know, the machine learning pipeline consists of data, like input data, data preprocessing, the model, and evaluation, right? So today we will talk about a kind of model that we could use to replace, like the kind of model that we could use, like machine learning model. In this case, we will talk about neural network. So last time we talked about linear regression, logistic regression. In fact, both linear regression and logistic regression can be formulated as a neural network. And we can, in fact, see the similarity by using the neural network architecture. But the difference between them could be that when we formulate a neural network, when we try to optimize for the model parameters, usually in neural network there will be like a computational package to do the backpropagation. And because of that, maybe we will get different weight if we were to use neural network for logistic regression task or linear regression task. You may not get the same model parameters, that's what I'm trying to say. But that's because they could be using like a different algorithm to optimize for the gradient to update the model parameters. Yeah, when they do optimization. Anyway, before we go over that detailed information, let's look over like an overview of what is a neural network. So neural network, you can think of it as like concatenated function. Let's say if you have input being x, right? Maybe this is better. Is input feature x. If you pass this input feature into, or maybe you multiply it with weight, right? And you get a result. Let's denote it as like the result of your first weight multiplication as h superscript l equal to 1. And the weight of the first, the set of weights, maybe the linear, let's say it's like a matrix multiplication with x, like this one is a vector, this one probably like a matrix. And the first weight matrix as L superscript 1. If you get these results from the first matrix vector multiplication and you use that result again, okay, and you multiply it with a different weight and you get result. And you do this multiple times. In fact, if you were to write like the whole entire function together, it will be like your output y here, y hat, will be equal to WL times W times, okay, maybe I'll just write it as like H L equal to L minus 1, like this first, right? But in fact, we know that this one is in fact WL minus 1, and it's WL minus 2 up until W1x, right? So it's like a function of function, and it goes as deep as how many times you do the multiplication. And if you cast this problem using like a neural network tool, you will see that in fact you can separate each weight matrix W as a layer. So the first one could be cast as like a linear mapping layer 1. Second one is linear mapping layer 2, or you can call it like a linear layer. So all of these linear multiplication, we call it linear layer, but it's like this is layer 1, this is layer 2, and so on up until layer L. And as you can see, the more layers you have, the more complicated the weights become, because it's like you multiply all the weights together. And somehow, if you look at this as a function of x, you can see that your output y is still a linear with X. But it's like, it's a linear in X, that's true, but the weight is extremely complicated because it's multiple times. And in fact, neural network utilizes kind of architecture to do the mapping of input to the output that are more complex. And that's why we start to say that, it could be data driven. Let's say if we would just try to optimize the view such that it maps Y correctly. If we were to do this, that means that we have, I don't know, it depends on the size of each view, but that means, the more the view we have, the more layers we have, the more model parameters will be. And yes, sometimes you can concatenate them up to, let's say, 10 millions or hundreds of millions. And when your model is that big, that means that you also need the number of training pairs to match that number of parameters. Because you can think of this as like if you have a linear system, right? And if you have like a large number of unknown, right? Then that means you also need a large number of measurements so that you can estimate for those unknown weight parameters. And therefore, the more data you have, the more fitted these model parameters will be for your data. So that is like the core idea behind it. In fact, people start to see that when we use model like this, it's actually quite powerful, especially when your data has certain behavior, or certain characteristic. But of course, if you can do correlation plot between your target and your input features and start to do some feature selection first and then apply this machine learning, of course, it could help you better than if you don't do anything about X. And the reason is because when you start to select input features, sometimes you will remove the confusing features out of the equation. But there are some people also say that those input feature X that you remove, sometimes they may contain important information. So some people still feel like it's better to include in. But I think this could be left as an open question, and you can find those answers by using validation, just like the one that you've done before with the linear regression task. That is, you can still use the feature selection as part of the process of trying to find, how big your X could be. And again, the validation could be used to find the number of layers. That's part of it too. Because if your number of layers is too much, right, you will end up having a situation where your model maybe give you a result that is far, far away from your solution, and that's because you have too much unknowns. But if your number of parameters is too small, then maybe you consistently get a result that is overly simplified, just like the high bias case. So it will go back to the previous topic that we learned about, the high variance and the high bias. It come back again. Like if your weight is too much, then very likely you could get high variance. But if your weight is too small, you again can get high bias. And in fact, due to the advanced, maybe architectural developing in neural network these days, there are so many ways that you could concatenate these layers together. For example, some people may be adding like a function, a nonlinear function to receive this linear multiplication. For example, that L superscript 1 could be like a sigmoid function that we learn in the logistic regression as well. So in each layer you can add like another function. It doesn't need to be just logistical regression. There's many function, nonlinear function you can use, like LeLU. If you heard of that before, yeah, LeLU, or maybe hyperbolic tan, or maybe softmax, or maybe sigmoid. Okay. All of these could be. But usually for softmax and sigmoid, and actually all of these could be used as a final layer as well if you want to map the output value to a certain rate. But usually the one that is used between, like let's say after you pass after you get this linear vector multiplication, you may want to pass it through a nonlinear mapping. If this nonlinear mapping is like in between, usually the types of layers that they will use are going to be the batch normalization and LeLU. And the reason is because the batch normalization will help normalize your data as passed through information. And LeLU would help, restrict the output from each layer to have only positive value. Sometimes it helps. Actually, batch normalization could help with when you compute your backward propagation. But because in this lecture, we won't go over that, but just know batch normalization could help. Yeah. And of course, if you have the nonlinear layer in between like this, then the relationship between y and x will become nonlinear, because that depends on how the activation functions behaving. Okay, so let's recap a little bit about the kind of output that we would get for each different task. For example, if we have an input feature of dimension Rn, and we feed this feature, let's say if n equal to 3 in this example, if we are using our neural network for regression task, right? Whatever input is, and let's say f is our neural network, right? The regression task need to provide the output that is of a scalar value. If it's a classification, then the output from this neural network can only be 0 or 1. If it was the multi-class classification, and this is a little tricky, your f could output y as like a numerical integer. Let's say if you have 4 classes for dog, cat, fish, and tiger, it could be y could be number 1, 2, 3, 4. Each integer is mapping to each class. That is possible as well. But the thing is, if we cast our output like this, there could be problems, because it's like our output will become integer value. And with that, you kind of need integer optimization to do the gradient, do the model parameters learning. And that's the reason why people will try to resort from this problem by using a one-hot matrix. One-hot matrix could be defined as follows. For example, if you want to represent class 1 for a dog, it could be like a vector of a vector where there's only one in a position that corresponding to class dog. And maybe a cat is like this. A fish, a tiger. Why? And that's the reason is because, this means that you are enforcing your neural network to only return the output of value between 0 and 1. You can do some thresholding to turn it from, maybe 0.75 to 1 if it's above a threshold value, let's say. And when you do something like that, it just means that, you can use simple regression, logistic regression technique to infer for each class. But of course, you have to think about how to exclude the other class if you only want to infer one. So this is going back to the technical detail of how should we learn multiple class classifications. And that means we need like a probability of class A, dog, probability of class cat, probability of class fish, and probability of class tiger. And this will change the function that we will use to represent the probability a little bit from last time. Last time we only do like 0 or 1, and if you remember when we do 0 or 1, we use logistic regression, right? We use a function that is like 1 plus e to the exponential x transpose beta. This is binary. And as I mentioned before, this could actually be reshaped a little bit to something like, maybe you can use like, in fact, you could kind of decompose them into some sum of exponential distribution. And then when you have this sum of the exponential distribution, if you could sum it to 1, then that means this is still could be used to represent your probability. And if you have multi-class, then that means you just further decompose this into multiple options, just like the example that I showed you before, like this one. Like you can start to decompose it into, let's say for each specific class there's exponential divided by sum of the exponential. So that is an alternative so that you can do the learning for multiple class. Okay. Another setting that is multiple label and multiple class. And in this setting, I would like to specifically go to this example. It's just like you have multiple places where your classifier can return the class. For example, if you are doing like a classification of the, like a costume or maybe the accessories that a person is wearing. The accessory could go from head, face, body, and feet, right? It depends on what they're wearing. Like, are they wearing nothing or are they wearing a hat? Or in the face, are they wearing glass or maybe earrings or nothing? On the body, are they wearing t-shirt, dress, or coat? And on the feet, of course, are they wearing shoes, socks? And just know that, this just means that you have multiple places. So that means if you have multiple places where you can infer a class, then that actually refers to multiple labels. It's just that for each place of that label, there are multiple classes. In this example, sometimes, like if you are kind of in a situation where it's a little complicated, maybe in some label, like let's say the label regarding to the face location, you have binary decision whether or not a person is wearing glass or not wearing anything. But for the other location, like the body, The person can be wearing nothing, maybe t-shirt, maybe dress, maybe coat, right? In this case, there are like 4 classes for the body, but only 2 classes for the face. So in cases like this, then your learning could be complicated. And yes, the reason that I bring you this, types of output for you to see in this lecture is because I want you to think about when your situation, your task is different, it's kind of go back to how you're going to shape your learning loss. And when you have this multiple label, how would you shape your learning then, right? It's possible in deep learning that you could extract multiple output from a neural network. For example, in this case, although I wrote it as F, but this F could be providing multiple output like F1, maybe just for the head location, F2, just for the face, and maybe F3 and F4 for the feet and body. Or you can force them to output as one, like one matrix, which could be, like a matrix like this. Let's say this is like a vector of, maybe a vector of the class index. Maybe, you know that the first index, it could go the value from 0 to 2, because it's like 0, 1, 2 for nothing, hat or beanie. And this one could go like 0 and 1. This one could be 0, 1, 2, 3. This could be like a 0, 2, 2, because it's 0, 1, 2. Yeah, you can output a vector like that too. But the thing is, when you have to do the learning, right? Again, there are some multi-class classification inside it. Therefore, for each of these vectors, it's better for you to turn them into the one hot vector, just like the one that we've learned before. Like in this case, it's better to turn it as a one hot vector. And in this case, if you turn this to one hot vector, then that means you will have multiple size one hot vector, right? For 1, 2, 3, 4, for 4 locations. But I will give you a hint. The simplest way is to enforce all of these labels to have the same amount of class, so that you just infer one matrix. So you will be size 4 times, maybe the maximum number of classes 1, 2, 3, 4, 3, so it's 4. So maybe you could do like a one hot. For one hot with the number of rows equal to 4 for the fact that there are 4 labels, and the number of class equal to 4 because the maximum class possible is 4. And then your output, maybe you start to restricting that output, let's say. For this one, maybe you're restricting it to have like, this one's always 0. And maybe just 1, 0, 1, or maybe 0, 1, 0, or maybe 0, 0, 1 for 3 class. So you may end up in a situation like this. And if you end up in a situation like this, that means that when you have an output matrix, you have to have a mechanism to enforce 0. Like this one, maybe you enforce 0 here. For this one, maybe you have to enforce 0 here and there, to still enforce a one hot vector for these 2 classes. For this one, you don't need to enforce anything, but for this one, you may still have to enforce it. Yeah, that's possible, a possible setting that could happen. Yeah, any question? No? This is just an example of how you may test your output for a neural network. And that also means that for each class, right, you just do like multi-class classification learning that probably 4 losses independently. Yeah, so you have to have 4 set of loss functions. So it's like multi-objective optimization. If you think about it, if there are no correlation between the features, but there are correlation in features because you're using one neural network. somehow your neural network will tie the correlation between each labels together. And so your optimization will look complicated, but everything based on one neural network backbone. Just a part. Okay. I think so. Okay. All right. So in here we will go through some common learning losses. Don't worry. These are just examples. Okay. Let's say if we have the view as a weight of the model parameters. Those are here, something like that. And you have your input that is X, and your target is Y, right? And your model will only give you Y hat. Usually, your loss function will be involved with trying to optimize your output Y hat. Try to optimize model parameters such that it give your Y hat to be something close to Y. That is like a generic formulation. And the thing is, I didn't write this explicitly, but just know that Y hat is equal to Fx. Okay? So somehow X is in here already in the loss function, but it's just embedded with the Y hat. And yes, as we mentioned before, there are many ways that output Y hat could be. It depends on the task. Like, it could be like a scalar measurement, like a real number, if it was like regression task. If it's binary label, then this Y hat will be 0, 1. If it was, let's say, multi-class classification, Y hat could be like a vector of integer in this case, or it could be like a 1 hot for C classes. Or if it's multi-label classes, multi-classes and multi-label, then your output Y hat will be like a matrix. Or maybe a vector of integer. That depends on what you're defining or what, the kind of task you're targeting. And for the regression task, and I believe this is probably the simplest, usually the loss function that we use are going to be either the mean square error loss or mean absolute error loss. And the only difference is like, are you going to use L2 norm or L1 norm to try to optimize the weight such that it minimizes the error. Okay? Meanwhile, for classification, in fact, we have done one already last time. That was the regression, logistic regression. You can use the same loss function and use logistic activation to construct your binary classification task. And of course, with that, I believe if you go back to our previous lecture, you will get this loss function. In fact, there are many other losses that you could use, like a hinge loss for classification, or you can try to cast as an F1 score. But be careful about one thing. Like, let's say if you use F1 score, you can see that your loss function could be quite nonlinear to Y hat, and then it will be nonlinear to X. And when it's strictly nonlinear like this, the optimization could be difficult. So that is something that you have to be careful about. Just like the hinge loss as well, when there are max function, right? You have to take a gradient. Then the thing is, your gradient will be compute in a sense of it's like it will be compute on a piecewise function. So that is something. So you have to think about the boundary and stuff. But because in neural network package, let's say PyTorch package, there is like a tool or maybe like a computational blocks that would do the gradient computation for you. So it will be simple in that case for you as a user. But if you think about what's going inside, it could be difficult. And finally, and this is something that we would focus on a little bit today, that is, if we have multi-class classification, And in this case, our goal is to be trying to cast the probability for each class. But don't forget that some of these probability have to be equal to 1, right? So with that case, we can use like an exponential function. And in fact, we can, instead of putting this as one hot, you can think of that if you have one hot that are linearly independent, right? If you sum them up together, right, it will be like a vector that, each column will correspond to each label. Maybe I'll just do another one. So each class, if you sum them up, each location of the vector will still representing that particular class. So if that was the case, we can actually write the probability for this vector to be like a probability of being in class A, being in class B, being in class C, being in class D, right? Maybe we approximate it as a probability first. And when we want to approximate it as a probability, maybe there's like a thresholding value, like to say, okay, if it's beyond this threshold, then we will say that this have a high chance to go into maybe class A, B, C. Then when that's the case, you can start to decide, which class it is. And actually for each probability, you can write it down like that, right? Because it's like you can represent this probability as some exponential function, then you can divide that exponential term for each class. Okay. When that was the case, right, when we think about then how shall we use this knowledge to then formulate our learning loss, then the thing is, it depends on what we have in our training set. So let's say if we have M training set, then that means that some of these M training sets will fall into class A, some will fall into class B, some will fall into class C. And with that, we could use the joint probability and decompose it. Okay, initially we decompose it with a log, in log space. But after that, we can start to group them into different classes. And this is like a general loss function when you do classification. And in fact, you can further simplify just like what we've done with the logistic loss function. It will turn into some cross-entropy loss. It will turn into something that looks like this. And it's actually also called a cross-entropy loss. Just go back and maybe have a little check of what cross-entropy loss look like. And on the internet, I think it's okay to just leave it as is. Finally, once we have our learning loss, our setting, another thing that we have to think about is, as the deep neural network could be, if there are so many layers inside neural network, thing is, you could take forever to run it. It depends on how many number of parameters are. The larger number of parameters, the higher chance that you will get like forever training with your training data, because the model will try to find the way to fit to your training data as much as possible. So because of that, it could take a very long time to train. And that's the reason why we still need the validation set to help us verify when our model starts to get overfitting. And in that case, just like what we've done previously, we have to have another set of data to be the validation set. And when our validation starts to increase from where it used to be, then that is mean that we should try to find a way to stop And this will be similar to the case where our generalization error will start to increase, and when it starts to increase, that means the model will be overfitting to our training. That's it. And I think for your homework, we will provide you an early stopper model to try and check how it works. So I think in this homework, you can do a lot of things. Like, for example, you can try to find the number of parameters, try to find the number of layers, and also try to use this early stopper. And the early stopper is kind of useful if you don't want to write your own, validation checking. It's already in our tutorial. And I think that's it. As I mentioned before, today lecture will be very quick. But anyway, let's go over this a little bit. Since some of our friends asked me this question, like, so what the convolutional layer look like? Okay, the layer that I showed to you before, that one that I keep saying that it looks like a linear regression, it's actually a linear layer, right? It's a fully connected layer. Linear layer is fully connected. But convolutional layer is different. When you apply convolution, it's just like when you apply convolution operation in image processing. That is like you have like a filter. Usually when we do, like a filtering on image processing, it's actually very similar to if you were to do the convolutional layer to the convolutional layer, and you just set the number of input channel to be the same as the number of output channel. Because convolutional layer work like this. For example, if you have input, let's say an RGB image, you will have 3 channels, just like what's shown here. If you are using a convolutional layer and you want the number of output channels to be the same as input, then you only need one filter set, that is this one. Sorry, the one on the left. You don't need the one on the right here. I'll just point it out. On the, you only need the view 0. You don't need the view 1. If you want number of output to be the same, the number of channels to be the same. Because when you apply filter the view 0, it will do that multiplication on 3 channels, and each channel will have its own output. If you have the view 0 and the view 1, then you will have another set of output. And that could mean that you will increase the number of output channels. But if you do another thing that is what we call like a 3D convolution. 3D convolution will actually have like a 3D filter, 3-dimensional filter, and that 3-dimensional filter will operate along all 3 channels at the same time. So that is the difference between 2D convolution and 3D convolution. And the thing is, 3D convolution will be very much different from the linear layers that we've used in your homework. You can actually read this page on GitHub to get more information. And I think, if I remember correctly, you can see the output 0 and 1 here. You can see the numbers actually changing when they change the filter. Then that actually means that you have actually 2 sets of output from here. If I remember correctly. Oh, it's not changing the number. But anyway, you actually will have 2 sets of output. So in this case, actually, you should have 6 output channels. But in here, it's only showing you 2. Okay, if you're not sure about what I'm saying, you can go over PyTorch. You can see that yep. So that's how the convolution is defined. So it depends on how many output channels that you specify. The more output channels you specify, the more, at the output times it will come. So that's what it is. Anyway, there are more than this. I think there are 3D convolution. Maybe not in this example. Okay, I think that's all. Just to give you some brief idea, but I think it's better to always go back to the instruction page of how to use that PyTorch operation, so that you will get the consistent result. Because sometimes for some tools they actually have different definition for this. And another thing, convolutional in 1D is actually similar to the linear projection. So that's an alternative way. Okay, I think that's all for today. Thank you for your attention.